Hi, today I was called out to do a bit of emergency fault finding on a lighting installation, somebody else's installation, not one of mine. And one of the problems was this was faulty. This is what we call in the UK an RCBO, which is a residual current circuit breaker with overcurrent protection. So it's basically a combination of a traditional overcurrent circuit breaker and a residual current device. Different countries have different names for these. Sometimes in the US I think they're called GFCIs, ground current fault interrupters, or earth leakage circuit breakers. They're sort of fairly common, but say the names can change depending on where you are. And it's got a handy little diagram on here to show you what it does. Basically, you have your incoming supply. It's got thermal and magnetic circuit breaker, and it's got this current transformer to measure any imbalance in the. Normally on normal circuit, you've got your mains coming in, and it should all go back out, the same way it came. If there's an imbalance between the current going one way and current going the other way, that means it's leaking somewhere, like somebody's touched it or there's water in it or something, which is generally a bad situation. So this current transformer measures that imbalance and then trips out the circuit to ensure safety. There's a number of sort of various markings on here, IEC 61009, which is sort of the standard that it's designed to. We've got the on-off, and this flag shows the actual status, because one thing about circuit breakers is they're designed that you can't just hold them on because they will trip internally. If I sort of move that slowly back, you'll see it will go to a trip state. So even though I'm turning it back on, it's still off, and it's showing that the green flag has to go all the way off to reset it. And there's a test button here. That's to test the residual current device. So if you look at this diagram here, you'll see there's this button here which just connects a resistor sort of diagonally across the current transformer to introduce an imbalance, but without causing any external leakage, because quite often you might find the button might be an upstream earth leakage breaker, so you don't want to trip that. So this just produces a local imbalance within the breaker just to test it. So the idea is that you, when it's on, you press that button and it will trip out. See, this isn't powered up, so it won't do it. There's a few other numbers here. So B10, that's the actual overcurrent category. 10 is the current rating, normal, so it's designed for circuits that run 10 amps normally is the maximum sort of working load. B is the time characteristic. So these have two aspects. There's a thermal trip and a magnetic trip. So the thermal trip is designed to operate on relatively small overloads over a long period of time, whereas the magnetic is designed to react to sort of high currents very quickly to prevent arcs and wires sort of exploding and so on. And the B is the current characteristic, the time characteristic of the magnetic part of it. So a B is a sort of fairly standard one that you use on normal wiring. The higher this letter, they come in C's and D's, and it's basically about surge capability. So if, for example, you've got a large motor load or a large number of switch mode power supplies with a high inrush current, you tend to use a higher rated breaker on those so that their switch on surge won't accidentally trip the overcurrent protection. One reason why this is actually quite important is that the main purpose of a circuit breaker is to protect the wiring. So let's say, for example, you have a massive great switch mode power supply, or more often a lot of small switch mode power supplies, which because of their input capacitor produce a fairly large current surge when you turn them on. Now one solution you might think, well, okay, we'll just put a higher rated breaker. The problem is that, let's say we've got, say, a 10 amp breaker, then our downstream wiring is rated for 10 amps. If, let's say, we put a 20 amp breaker, we'd have to uprate all our wiring so that the wiring could withstand 20 amps, because that's the purpose of the breaker. So even if our power supply is normally only around, say, 6 amps, if you uprated this to a 20 amp breaker, you then have to uprate all that wiring, which would be a real pain if it's particularly for a long cable run. So what you do instead is you use a C or even a D breaker so that it withstand that surge, because for the surge current for a short period of time isn't a problem. It's not going to set the cable on fire because it's a heating effect. So if this conducts 4 or 5 times its nominal current for a few hundred milliseconds, that isn't going to be a problem because it's not going to set fire to anything. So for that sort of load, you use a C or a D breaker. There's a few other things on here. There's this is 10,000. Now that's its peak current surge capability. So basically, if you have like a really hefty incoming supply, obviously these things could be used on distribution boards fed from massive bus bars capable of huge amounts of current. So if there is a short circuit on the output for a short amount of time, a very high current can flow. in between the time that current starts and this breaker actually trips out, because obviously it's a mechanical device, so it takes a finite amount of time for it to trip. So that's basically its maximum current rating to guarantee that this thing won't just catch fire or explode or sort of generally sort of cause mayhem. Now these are typically installed in a sort of distribution board, and quite often there's like a bus bar that's just got tabs on it, so this actually screws directly onto the feed bus bar. There's a neutral wire, because of the residual current capability, it needs to have the neutral so that the neutral comes in, so it has the live and the neutral for this current transformer, but this is only used for the residual current device. This one's also got a functional earth connection. Now they don't all have these. The purpose of that is mostly so that the RCD protection will still work in the case of a neutral fault. That's, from what I can gather, it's a little bit unclear as to whether the standard requires it or whether it's required to meet the standard, or it depends on the hardware. I'm not entirely sure of it, but there's also the aspect that the coincidence of a neutral fault and an RCD fault is maybe fairly unlikely. So that's something they don't all seem to have, and so we'll take a look inside and maybe see if we can figure out how this is actually connected and how it works. Right, now when we open this up, there's actually quite a surprising amount of stuff in here. For something you think, oh, it's just a circuit breaker, it just trips when the current goes over. You might think it's quite simple, but actually there's quite a lot of subtle things going on here. So because the RCD and the overcurrent protection are effectively sort of completely separate circuits, if we look at the RCD stuff first, so we've got the neutral wire coming in, goes through the current transformer and then goes out on this terminal to the load. The live comes in. I'll deal with the overcurrent section in a minute, but basically the live ends up coming out here, again through the current transformer, and then to this tab which is connected to the live load terminal. So this one, actually, once I opened it up, it actually seemed to start working again, so I don't know if it was mechanically jammed or something, but electronics do still seem to work. And the RCD trip is actually this coil here. So basically we've got a quite complicated piece of mechanics. So this is the magnetic part of the overcurrent protection. So if you get too much current, this solenoid pushes this little lever through, and if the RCD trips, this solenoid operates and pushes this through and then trips it. So if we just turn it on, so this pushes through, that just trips it out. And the overcurrent side of things, so we've got the live comes in here. The first thing that happens is it goes through this bimetallic strip. So this is the thermal protection. So as the current increases, this will start heating up and it will start to bend in this direction until it pulls this lever. So if I just reset this, it's a bit hard to hold it set because I haven't got the top cover on, and some of these shafts actually lock into the other side of the cover. But if we just set that, so what will happen is, this heats up to the point where it pulls this and releases it. It then goes through this sort of soft, basically flexible wire to here. So this is one of the actual contacts, and this is the other contact. I'll talk about this stuff in a minute, but the actual sort of current goes through here, across here, up, and then through this sort of coil. So obviously this is a big chunky coil, so this is the overcurrent protection. When the current through this coil gets too high, the magnetic field causes this lump of metal to go in and trips it out quickly. And obviously on a higher current breaker, this would be a much thicker cable, fewer turns of a thicker wire, and that's what then goes out. Now this is the interesting stuff, because of course if you've got a high current circuit, when you turn it off, what happens, or what can happen, is you get an arc forming. So as this contact opens, let's get it closed. So as that starts to open, you'll start to form an arc here, and in the worst case, typically with an inductive load, as this distance increases, it can actually sustain that arc, because once it's at the point it breaks, you can get a very small spark due to quite often just local heating, and that heats up the air and effectively turns the air conductive. So as this opens, you get this area of sort of conductive air, and because that's not as conductive as the metal, because it's resistive, it can dissipate quite a lot of power, so the voltage across it will increase, but you've still got substantial current flowing through it, so you actually can get quite a substantial amount of energy produced. And so as this carries on open, again in the worst case scenario, the arc is still continuing by the time it opens, and the geometry of this is designed so that the arc actually transfers to this strip. So we've now got this arc across here. Again, at some point this arc will extinguish. There's a big difference between AC and DC breakers, and the thing about the AC, because the current goes to zero every half cycle, that will generally tend to extinguish the arc, although you can get some residual gas sort of floating around. It will typically extinguish, if not on the first half cycle, within the next one or two. But say if we carry on and assume it's still arcing, say that arc will potentially travel down here. And arcs tend to like to open up. Obviously you've all seen Jacob's ladders where you get sort of the spark, the arc increasing as it sort of, they just tend to like opening up. So the arc will travel up here and then into this part here. Now what this is just a stack of plates. These are copper plated, but they're actually steel plates. And the idea is that once it hits here, the distance is actually quite small. So what you'll get is lots of small arcs, so that energy is dissipated over a wide area. And because this is sort of fairly substantial chunk of metal, it will cool that air down to quench that arc as quickly as it can. So it will take, you need a massive amount of energy to actually sustain the arc within this area. But you'll notice that over here we've got these horizontal pieces, and these are actually a vent, so that in the worst case we get just some colossal amount of energy arcing over in here, instead of the whole thing just catching fire and exploding, it actually directs that blast down these slots here and out to this sort of hole in the back. So this is basically a phenomenon known as arc flash, which can actually be very dangerous. People on large switchboards, a really bad arc flash can actually be fatal. People have actually died from it. So what happens is, if this does go into a really bad arc flash situation, again we're talking about this sort of 10,000 amp sort of rating, that energy is pushed backwards first, so that if some guy's working on the switchboard, the energy is, it's got a nice easy way out rather than forcing its way out the front. The other thing that you see on here, there's both in here and here, there's these sheets. Now some circuit breakers actually have ceramic, but this actually looks like plastic, but it does look like it's a different type of plastic to the main case. It feels like it's maybe quite heavily glass filled, so again that's to do with, if you've got an arc here, preventing this sort of, basically melting its way through and possibly onto adjacent circuit breakers, or generally sort of out of it. So this is some protection. This does actually feel quite hard. It is a plasticky material, but it feels like a very heavily filled plastic material. You can just hear how it sounds different when you tap it. So that's some additional protection on there. Now this is the chip that's used in the RCD section. Now some RCDs are actually completely electromechanical, but nowadays, as with most things, it's generally easier to do stuff electronically. So this is a dedicated chip for that function. Interestingly, because obviously you're detecting quite a small current through that transformer, so it's actually got quite high sensitivity. It's got a threshold of about 6 millivolts. And if we look at what's inside this, we've got some power supply regulation stuff here, an amplifier, and then an output driver. And if we look at the typical circuit, it's sort of fairly straightforward. So we've got our AC supply here. This is the actual trip coil. So what it looks like they're doing is they're actually using the resistance of that trip coil as part of the voltage dropper to provide the low voltage supply for this. There's also this sort of resistor and capacitor here, and we've got our current transformer input here, and the output actually goes to this thyristor. So what happens is when it trips, it basically shorts out this supply, which provides a high current through this trip coil. So we've just got this simple, basically a two-wire connection to the mains, and then we've just got the current transformer thing. So the connections are sort of nice and simple, and it's just fairly simple. Just as soon as it fires a pulse there, the whole thing just goes short, puts a nice high current through that trip, and because of the way it's arranged, that current will sustain through that coil until the thing switches off. I would imagine that if it didn't trip, this coil would probably get quite hot quite quickly, but because the thing is on the far side of the circuit breaker, the idea is it will trip, but it means the coil will just keep trying until it does actually trip. This is just an MOV surge suppressor to avoid damage and sort of false trip, so it's sort of fairly simple circuit in there. Just taking the LCD board out to take a look at it, see what they're actually doing with this earth, and actually yes, it is very straightforward. All they're doing is if you take the reference circuit, they're not using the bridge rectifier, they're using half-wave rectifier, and literally we've got a supply from both the earth and the neutral, and we've got these 3 MOVs just connected sort of in triangle form across those 3 pins to provide protection for any transient. So yes, the earth is just simply a backup supply, so the thing will still trip if the neutral fails. One thing I was a little bit curious about, this is a 3.9k resistor that looks a little bit crozzled, and this is the current limiting resistor for the test button. Now, you wouldn't think, you know, that should only be operated sort of for very, very brief periods of time, so it's a bit curious as to why it's actually burnt. Now, if we work out the current, so that's 3k9, so at 240 volts that'll produce 60 milliamps of fault current across the transformer, so that's twice its rated trip voltage, so that's probably just to make sure it trips. I think the tolerances on RCD thresholds are actually fairly wide. I can't be bothered to actually go and look at what they actually are, but they're probably in the sort of several tens of a percent either way, I would imagine. Particularly because early ones were sort of electromechanical, so probably quite hard to make accurate. But the actual power dissipation of that when it's conducting is about 14 watts, so it probably wouldn't actually take very long for that to get very hot. So I think we should maybe try that and see how long it does actually take to get hot. So let's see what happens when we do connect the resistor straight across the mains. Yes, it doesn't last very long, but I'm still a little bit surprised that it got hot enough to show burn marks just from the occasional test button operations. But then again, actually having said that, this breaker was actually faulty, it wouldn't trip, so that actually would explain it, because normally you'd press the test button, it would trip instantly, so you'd get hardly any power dissipation in that resistor. But because this breaker wasn't tripping, you know, you'd hold the test button and it would actually put power through that resistor, for as long as you held the button. So think about it, that actually explains exactly why that resistor was burnt, purely because the thing wasn't tripping. And just underneath here you can see the contact that the test button uses. So the test button sits, just sort of fits in there and just pushes down this contact just to provide that bypass that current flow around the transformer to trip it. So that's not actually part of this mechanism, it's just located here because it's mechanically convenient. Obviously it's only this top bit that actually goes through the front panel of the switchboard, so this button needs to be accessible. Interesting little detail how this this front panel indicator works. You can see it's got this sort of big hole in it, so it only changes state once the contact is fully engaged. So basically it fully turns on before it's a bit hard, because this hasn't got its top on, it's a bit hard to do this, but say as it turns on, it's only when it gets all the way on that it starts moving that flag, and then similarly when it turns off, it only turns off once it's gone all the way back to the fully open position. So this doesn't go green until this contact has gone all the way back to its fully open position, which is obviously a safety feature. So I mean, you could imagine a scenario where this actually welds together. Obviously these are designed not to do that. We've got we've got quite a heavy spring pushing this, actively pushing this open. But you could potentially have a situation where this could weld itself solid, and then at least that indicator would tell you that it isn't actually it hasn't managed to turn off. I just actually noticed when I was putting this back together, there's actually a little piece missing. This little piece here. What this does is just close it. You see the contact starting to close, but then it pauses until the switch is all the way in, and then it suddenly snaps down. So any small amount of arcing you get when the contact closes, it minimises that time to avoid the risk of the contact welding shut. Right, I've just chopped off a piece of the other half, so we've got the supports for the ends of the shaft. I'm going to actually have a quick play with this and see how it works. Right, now to test this we need a nice sort of high current AC supply. The easiest way of doing this is just using a transformer, because obviously the circuit breaker doesn't really care about the voltage, it only cares about the current. So I've got a toroidal transformer that I've wound a few turns of heavy gauge wire through, and this is just connected up to a variac so I can adjust the current. You can do this with any big transformer. The nice thing about the toroid, it's already got the hole through the middle, so you can just wind the wire through. You know, you can use something like a microwave oven transformer if you take the high voltage secondary off, and people have used those for doing spot welders and so on. But I just had this to hand. It's easy because you don't need to unwind anything. And so this is just showing the input current and the output current on this clamp meter. So as I crank up the voltage going in, you see we can get up to 290 amps, and our input current is only about 1.5 amps. Hear a nice hum. You can actually see this little wire, sort of. You can actually hear it. You can hear it buzzing. You can actually see it moving as you turn the current up to an extent. You can sort of see that. Just purely from the magnetic effect of that. Obviously, this wire will get and this is actually really hot just in those few seconds. So you know, this is only suitable for sort of short-term tests. Unless you use much thicker wire, and that's almost too hot to touch just after those few seconds. So that would start smoking fairly quickly. It's not really rated for 300 amps, that cable, but it will do the job for the moment. Right, so if we look at the thermal aspect of it, I've got to put this cover on because these guides hold this pin in place. But what we see is as we increase the current, you'll see this strip bending to the left until it pulls this lever and opens the breaker. So if we go up to sort of 10 amps, that's its normal running current, so it should sit there pretty much all day long. As we increase it, we should start seeing this strip bending over to the left. It's 20 amps, and there we go, tripped. And if we give it a higher current, we should see most breakers will actually have their data sheet will have a curve showing the time, overcurrent versus time. So the higher the overcurrent, the quicker it will trip. So if we take this up to a higher current, 30 amps, trips fairly quickly. That buzzing was just this car rattling around because this hasn't got the cover on. Some of these parts are a little bit loose, so it sort of makes a bit of a growling noise. So now if we look at the magnetic side of things, what I'm going to do is I'm going to turn the variac sort of fully up, so this will put about 280 odd amps through as soon as I hit the switch. And what we should see here is that all won't have time to move. This magnetic thing will just trip it out pretty much instantly. So if I just turn this on, bang, instant trip. Now obviously because we've got a low voltage, we've not got any arcing going on. So I think we should see if we can investigate if we can actually produce some arcing over there to maybe try and demonstrate. I'm not sure if we'll actually be able to get it, doing the whole sort of going into their thing, but I think we'll give it a good go. Okay, so what I've got here is an oil burner ignition transformer. This puts out about 10 kV at about 20 milliamps. So we can sort of create a nice little arc with that. This is sort of quite likes to expand. Let's see what happens if we put that across our breaker contacts. I'll just clamp this down so I can operate this with a stick. So I've just connected that high voltage across it. Let's see what happens when we break it. Okay. So the arc doesn't seem to really want to go around that corner, but obviously this is a very different type of arc to what it's and you can see it's sort of trying to go around there, but it's not really I think it hasn't really got the energy. I think a real arc would have be out spewing out lots of energy, and it would actually just the whole thing would just expand in here, but obviously this transformer isn't actually putting out a great deal of energy. So let's have a look at something that maybe can. Okay, those of you that know my website of old may recognise this. This is the Destructotron, which is basically a large high voltage capacitor bank capable of discharging huge amounts of energy, just like the sort of surge you might get if you connected a circuit breaker to a sort of high power main supply and shorted it. So we've got basically this is a bunch of capacitors from old defibrillators. There's a high voltage transformer that's just 2 microwave oven transformers, and there's a high current contactor, or just a set of contacts that are solenoid operated, and some just rectifiers down there. So let's go look at my website and find, you'll see some other stuff that I did with this years ago, so I sort of dusted it off, and let's see, in a fight between the Destructotron and a circuit breaker, let's see who wins. And the way these are controlled, there's obviously a remote control, because you don't often want to be too close to things when this thing goes off. This button just holds the contactor open, so you let go and it shorts it, and it connects it both to the terminals, but also connects a discharge resistor, because quite often whenever you're connecting these two will just disintegrate, so you want to make sure the capacitor ends up discharged. And then when that's open, there's just a momentary switch to start charging, so you can see the voltage going up, so you can charge it and then release it off and it will discharge. So the idea is that, you know, if you let go, it ends up in a safe condition. It's not charging and it's discharging. So I just screwed this down to the bench just to stop it jumping around. One issue when you put it dealing with high surge currents is that things do tend to bounce around a bit, even wires. I mean, quite often the wire will actually twitch because of the magnetic field it generates, or repels itself. So if you've got like a coil, it'll actually have a tendency to try and uncoil itself. And I've just put a couple of screws in the top just so that the mechanism works. I've put some fairly strong lighting on this, hopefully, so that any flash doesn't blind the camera too much. Let's give it a quick shot. Okay, so that trips, so let's crank the power up. That works. Now, unfortunately, this has done a bit of fairly serious damage. It sort of disintegrated the coil. We can see some of the sort of flash. We've got some sort of pitting of the contact, and we can see a bit of the arc flash, sort of, which deposited some metal on here. Can't actually see any evidence of it having travelled down or into here, though. I think it's just everything just went off a bit too quickly. So it's possibly not quite the sort of surge it was designed for, but right, so I've got this other one. Let's just try this and see if this I'm going to try this at a much higher power and see if we get any venting out that bottom, and then we'll do a post-mortem to see what it's looks like inside. So it's going to be at quite a lot more power than the previous one. It'll make quite a loud bang. Oops. So that was maybe a little bit more than I was expecting. It managed to take down the fluorescent tube that was overhead. I did feel a little bit of shrapnel hitting me. Fortunately no major injuries. I think we need to take a closer look at what's happened to this. Obviously I think this is possibly slightly in excess of its rating. I would certainly hope so. But let's have a look through the debris. Right, so if we look at closely at the wreckage, the main destruction I think has actually been the coil disintegrating. As you can actually see, these are some of the windings of the coil, and they've actually dug a hole about 4mm into the bench. I'm leaving this as is. I'm going to take it all, pull it all off in a minute. I'm trying to try and preserve the crime scene, as it were. But I don't think that dent was in the bench before. If it is, it's just a very lucky coincidence. But you can see the wire has actually straightened itself out and dug itself right into the bench to, it's probably about 5mm down into the wooden bench. There's also some of the wire here. I'm not sure how clear that is, but it looks like the profile's actually flattened it. Yeah, it's actually flattened itself out somehow. Yeah, you can see that's actually a flat surface. There's a bit that's just sort of come off, and you can see there's just pieces of, loose pieces of wire in there, just fragments of that coil. It's just ripped itself to pieces from the surge. So it's picked. So you can see the slug from the solenoid has just come out completely. In fact, most of the solenoid and the solenoid coil has basically just completely disappeared. I think that's part of the forming. See sort of all the copper that's been deposited on there, vaporized copper. So the slug's just sort of fallen out. And so we've just got all these little fragments of copper, which say you can see they've flattened out. In fact, look at that, that's really gone sort of super thin. Just presuming the force that it's, because say what happens is that the magnetic field in the coil, each piece of wire basically pushes away from everything else, so it's just trying to just get away from itself, just with so much force that it's just completely disintegrated. I wonder if some of this, because copper does tend to harden under sort of extreme force, and in fact this flat piece, this is very, very hard. It's much harder to bend than the other bits. I think we've got sort of basic work hardening of the copper. That's become very, very stiff. I can't bend that at all. Again, there's some amount of flattening. So I think this flattening is where it's just flung out and just hit something and just flattened itself out on whatever it's hit. A few more fragments there. And obviously it's just shattered the plastic from the just the force of the impact. Again, I think this is probably shattered mostly purely from just the impact blast rather than the arc blast. Yeah, well, actually, there is some evidence of arcing. You can see on here there is actually some arcing on these pieces. So it looks like the arc did actually make it into this section to some extent. You can actually see the where it sort of burnt through the copper plating on there. Let's take apart what's left of the casing and have a close look at that. So actually looking at the damage on the bench, some of these are actually wedged in so hard I had to use a pair of pliers to get them out. There's actually still a piece in there. It's actually dug itself in, but I mean that hole is about sort of 6mm deep or so, and also it's compressed bits of the plastic. So these white bits here are sort of fragments of the plastic case that it's pushed into it. So there's a few sort of fragments there. So if there's that amount of force there, I was looking to see if I can find any. Other evidence. And actually, if we go up to the ceiling, actually see a few bits of wire embedded into this wooden ceiling, so I was sort of quite lucky to get away without any serious injuries on that one. I think it was a surprising amount of force, and so it was the coil that went, which I just wasn't expecting. I was just expecting lots of arc flash. So let's dig this out of the ceiling. That's dug itself quite in, and again it's flattened out the copper. The only bit I could see is a few other dents, but this is just thin foam, so only the dents in here could have been there beforehand. And if it did hit this, it would have gone so deep that you wouldn't actually be able to see it on the surface. Another Another piece there where it's dug itself in. And of course it took out the fluorescent tube. Not sure if that's a mark from where it hit or just a mark that was there before, but it's probably in about the right trajectory. There's actually a slight dent in the metal there. Now, pretty much all that damage was in the coil section, and the actual contact section hasn't quite disintegrated, but we can see some evidence of some sort of blast coming out of here. So let's take this apart and see what we can see. Now obviously we've got a lot of pitting on the actual contact there. That's sort of very sort of pitted and generally knackered, but you can see some evidence of blast sort of extending down to this part. Again, you've got sort of lots of metal deposited on the case. And looking at this piece, there's actually evidence of arcing, some sort of certainly blackening here, but there's also sort of some sort of evidence that something's going on. I don't know if that was arcing or just mechanical distress. So, but same, yeah, I think obviously once that coil went, this whole thing would have been just mechanically in disarray. But so there clearly has been some quite significant amount of arcing going on in here while that was happening. Now, of course, this probably isn't a scenario that these are designed to take, because the thing that causes all that destruction with the coil is the fact that it's coming from a very low inductance source, which means the rate of rise of current is very high, and that's what does all the damage. You know, the rate of change of current is what creates this moving magnetic field that causes all the destruction. And obviously in a conventional situation you'd have much longer sort of feed cables, even though the actual supply impedance might be quite low. The inductance would be high enough that the rate of rise of current wouldn't be enough to actually cause the coil to disintegrate like that. That's pretty much a mechanical disintegration, not an electrical one. It's purely the forces that are set up by that massive magnetic field just physically tear it to pieces, and obviously as it's coming apart the pieces will then maybe arc to some extent, but the primary sort of destructive force is purely that magnetic mechanical force, which is difficult to measure, but I'm sure it would be in the range of thousands of amps within sort of microseconds or so. So extremely high, generally fairly ridiculous. Looking to see whether this, what if this wire's maybe folded itself up a little bit as well. That's actually, that wire seems relatively unscathed. Let's take a closer look at the wire. This is the wire from the first one that I did, which wasn't so badly injured. So you can see it is just normal round wire that's sort of fairly easily bendable. But then we've got some of these fragments which are, they're flattened to almost rectangular cross section, and so they've become very hard. I mean, I cannot bend that at all. It's just got so hard from the the impact. I assume it flew out and then impacted, and just sort of kept going and flattened itself out and sort of hardened in the process, and that is virtually unbendable because it's just got so hard because of that impact. So that was an interesting little experiment. So we went a little bit over the top on the testing. It would actually been quite nice to have access to a nice sort of high voltage AC, high current source to look at that arcing thing, but I think obviously it needs to be, the actual magnitude needs to be fairly sort of carefully controlled and measured, and didn't immediately have any facilities to do that, but at least it was slightly entertaining, and say fortunately apart from a minor scratch, no major injuries. I did try doing some high-speed camera footage of just a reconstruction just using a coil, but it was just, the camera just wasn't anywhere near fast enough. All you see is like one frame of flash and then bits flying. I think to actually sort of capture the motion of the coil, you need to be way up into the tens of thousands of frames a second category. So I mean, if anyone has access to a camera that will do that sort of speed, then it might be interesting to do some experiments. But say the camera I've got, it will do sort of 1,000 frames a second full frame, and sort of partial frames down to 5,000 frames a second, and you just don't see anything really on that. So you need something a lot faster to be of any use.